In this video, we're going to be just going over those 8 practice problems. I'll be going over them with you. I recommend you try them all on your own before you watch this. And if you're really having trouble, you can follow along with me, or you can try to complete these after you've had the class with me and we take those notes. So your choice. So we're going to just do those same exact 8 questions that we completed and found the shape, because understanding the shape really kind of helps us figure out where the electrons are being drawn to. So here we had carbon dioxide. It's linear. If we want to take a look at the bonds, we actually have some polar bonds here. So between carbon and oxygen has that higher electronegativity. So electrons are going to be pulled this way. And between this carbon and oxygen, electrons are going to be pulled that way. However, if you take a look at that, they are drawing exactly opposite directions. They're going to cancel out. And this would be a non-polar molecule. So even though it's got 2 different polar bonds in it, overall they cancel out and it is a non-polar molecule. All right, so let's take a look at the second one. And this is why shape's really important, because here I drew it all in a straight line. When we look at it and we want to be able to picture where that dipole moment is moving, where those electrons are getting pulled, we really need to draw it in a more accurate way of the shape. So I'm not an artist, so I'm just going to draw it, with a bend like that. This is a bend right here. And again, this is also correct. It's just harder to picture it when we're drawing where the electrons are getting pulled. So you can imagine this, we just kind of flip it sideways a little bit and it'll look exactly like this. So it's a bent molecule. If we take a look at each bond individually between hydrogen and oxygen, oxygen has that higher electronegativity. So it is getting the electrons drawn to it. And if we wanted to draw our overall dipole moment, where are these electrons getting pulled? Directly towards the oxygen, like that. So that's where our electrons are getting pulled. If we wanted to draw the partial positives and partial negatives, each of these hydrogens is going to be a little bit of a positive, and this oxygen will have a partial negative. And again, I want you to remember, it's a neutrally charged molecule. So if you add these 2 partial positives and that partial negative together, it'll equal 0. We don't need to know the exact numbers here, but just know that when we add all the charges up, it'll come out to 0. So this is a larger partial negative than either of these partial positives. All right, move into 3. All right, so this one is Trigonal Pyramidal. If we want to take a look at these bonds, hydrogen and nitrogen, nitrogen has that higher electronegativity. So between the hydrogen and the nitrogen, that nitrogen is going to be pulling those electrons towards it. So if we wanted to draw that overall dipole moment, it would start, remember these are all forming like a triangular pyramid, so it would start in between all of them and go straight up through the nitrogen. And that's where those electrons are being pulled. And then if we wanted to put those partial charges on here, this nitrogen has that partial negative, and that partial negative is going to be exactly as strong as all these partial positives where the hydrogens are added up. So because we got the partial charges and the dipole moment, Remember, those come together. When I say they come together, I mean we have them both at the same time. Whenever you got a dipole moment, you're going to have those partial charges. Because we have both of those things, this is a polar molecule. And I forgot to write that down with this second example. We had those partial charges and that dipole moment. So water, H2O, is also a polar molecule. All right, so we've done 3 of our examples. 5 more to go. All right, so this is a nice small molecule. We just got 1 bond between 2 oxygen atoms. So they're the same element, same electronegativity, nonpolar bond. When all your bonds are nonpolar, your molecule is going to be nonpolar. So that's kind of a useful thing to know. When all your bonds are nonpolar, your molecule will just happen to be nonpolar as well, because no electrons are getting pulled in any direction. So nonpolar molecule O2. What about this next one? We got CH4. This is methane. It forms a tetrahedral. And if we take a look, our bond between carbon and hydrogen, they're pretty close together. They're not exactly the same, but we're going to say they're pretty close together. So all the bonds are individually nonpolar. No electrons really getting pulled in any direction. It's going to be a nonpolar molecule. All right, a few more. This one's trigonal planar. And if we want to take a look at each of these bonds, we got some hydrogen-carbon bond. And again, you're going to see this a lot. That's always a nonpolar bond. So we don't got to worry about those. Carbon and oxygen, though, that's polar. So let's take a look. Oxygen has a higher electronegativity. It's going to be pulling those electrons closer to it. So let's draw our dipole moment. And we only got 1 arrow. When you got 1 arrow, dipole moment's easy. Just straight there. And then we can draw, well, it's not a very straight line, but straight up towards that oxygen. We could draw our partial charges, and we'll have a partial negative up here by the oxygen, and this carbon will have a partial positive by it. And when we got those partial charges, that tells us polar molecule. All right, this one's a bit of a tricky one here. All right, so let's take a look at this one. It's actually bent, so it's better if we use something that's more accurate to the actual shape right here. So we'll use that. And if we take a look at each of these bonds, the hydrogen and the nitrogen has a higher electronegativity. And if you take a look at the nitrogen and the oxygen has even higher electronegativity. So now this is where we have to start adding vectors together. So you take a look, it's got some movement in this direction, it's got some movement in that direction. And overall, our movement of electrons isn't going to be straight up towards that oxygen, but it'll kind of be, you know, you gotta use your artist's hand here. It's up, but then down and in this way and a little bit. So we're just gonna kind of draw it towards the oxygen, but not completely towards the oxygen. It's a little bit down towards the nitrogen as well. So overall, this is our movement of electrons. And if we wanted to draw charges, definitely the O would be partial negative, and definitely this H over here would be partial positive. In here, it's a little bit iffy because it's pulling and losing electrons over here. Don't worry about that too much. As long as we know that there's partial charges, that's the main thing. that'll tell us it's a polar molecule. All right, so last question here, linear molecule. So everything's in a straight line here. Take a look at each of these. We got hydrogen and carbon, non-polar bond, so don't gotta worry about that. Carbon and nitrogen, they're both right by each other. Nitrogen has that higher electronegativity, so it's pulling some electrons that way. That'll give the nitrogen that partial negative, and the carbon right here, a little bit of a partial positive. And if we wanted to draw the overall dipole moment, it'd be that direction. So towards our nitrogen, that's where our electrons are getting pulled. And because we know the electrons are getting pulled in a specific direction, they're not evenly shared. That tells us we got a polar molecule here. And in the coming weeks, probably the next 3 weeks, we're going to be looking at the importance of knowing whether a molecule is polar or nonpolar and how different those properties are that they have, because being a polar molecule gives that molecule very different properties than a nonpolar molecule.